Hello everyone. In this video, we are going to solve leetcode 2812. Find the safest path in a grid. In this problem, we are given a 2D matrix where the cells contain only the values 1 or 0. 0 meaning the cell is empty and 1 meaning there is a thief in the cell. We can move from one cell to its adjacent cell in all the four directions. We are supposed to find the maximum safeness of a path from the top left cell to the bottom right cell of the matrix. Here, the safeness factor is defined as the minimum Manhattan distance between any cell in the path to any cell containing thief. Here, the Manhattan distance between any two cells, basically x1, y1, and x2, y2, is x1 minus x2 mod, basically the absolute value, plus y1 minus y2, absolute value of this. Let's try to understand the question using this simple grid. The thieves are in the cell 03, 10, and 30. Now, what we are going to do is we are going to find a path from the top left cell, which is 0, 0, to the bottom right cell, which is 3, 3, where the safeness factor of the path is maximum. So, what is the meaning of safeness factor here? According to the question, it is the minimum Manhattan distance between any cell in the path to any thief in the grid. So let's see the grid which represents the Manhattan distance. For all the cells in which there is a thief present, we have given it as a 0, as the Manhattan distance from the cell where a thief is present to the cell is 0 if this cell is present in the path. Now we need to select a path, let's say from this point to this point, where the safeness factor is the maximum. So let's say we chose this path, which I am following with the marker right now. In this path, the minimum value is 0 because I'm going through a cell where a thief is already present. So, so the value for this or the answer for this path is 0. Let's say I chose this path. Now in this path, the minimum value which I can find is 1. Let's take another path. In this path also, the minimum value present is 1. Now we can see that the maximum value that we can have for a path to reach from 00 to 33 is 1. So 1 is the safeness factor that we can have for this grid. Let's take the example that is given in the question. Now for the first example, we can see the thieves are present in the start, basically the source cell and the destination cell. So even if we want to take any value for the maximum safeness more than 0, we cannot because the thieves are present from the point where we need to start. So that is why the answer for this grid will always be 0. Let's take the another example that is given in the question. In this grid, what we can see is there is only one thief present and that is only at the cell 0, 2. So the corresponding Manhattan grid will be there is a path that I am following currently which has the minimum value in it as 2. Let's say I try to follow this path. Here, I am going through the cell 1, 2 where I have the value 1. So the value of this path will become 1, minimum value or the minimum safeness. If I want to go through this path, now I'm encountering a 0 in my path. Hence, it will make the safeness as 0. In this way, I can see that I can have a value which is 2, and that will be my maximum safeness for the path in this grid. Let's see the final example for this question. For this example, we can see that in the right we have the Manhattan grid for the respective example that is given in the left. So there is only one path, or you can say the path which can have the maximum value or the maximum safeness as 2 as the answer. There can be multiple paths, not one path. Yeah. We can divide the problem into two parts. First, creating the Manhattan grid, and the second, finding what is the value or the maximum value that we can have from going to the cell 0, 0 to the cell n minus 1 comma n minus 1. These are the two subtasks that we need to complete in order to get the solution for this problem. So let's see how we can get this Manhattan grid for a respective input grid that we are given. Let's say we have been given the grid that is this grid. Now, how can we find the Manhattan grid for the respective input grid? Now, what I can do is taking the cells which are having thieves as my sources, and then from these cells, if I run a multi-source breadth first traversal, then what I can find is I can go to this cell from my current cell to the left and to the right. Similarly, I can go to the left, to the right, down. From this cell also, I can go to the left, but this left is already visited, so I won't go, but I can go down. Now, in my queue, which I'm using for the BFS traversal, I am having these cells right now. Now, I will have a counter. Let's say the counter is C and T. Initially, the value of the counter will be 0 for all the cells which are having thieves in them. Now, after one iteration, the counter value will become 1, and I will be present in all those cells that are adjacent to the cells having thieves in them. So currently I'm having these cells in my queue, and the corresponding value for these cells are 1. From these cells I can traverse to this particular cell. Whichever cell I'm marking right now, I can traverse to those cells from the previously present cell. Now in the next iteration, the value for all the cells will be 2. In this way, I can calculate my Manhattan grid. And using that Manhattan grid, let's see how can we solve or how can we get the maximum value of safeness for a path to reach from the source to the destination. Let's say I'm having a Manhattan grid as this one, which is being represented here. So what I need to do here is I need to find a value, or let's say a max safeness value for which I can go from the source, which is 0, 0 to the destination. So let's say I'm having the keeping the value as 2. So what this means is whichever cell I visit, the value for the safeness should be greater than or equal to 2. It cannot be less than 2. So can I uh, stay in the source for this value? Yes. Can I go to the adjacent cell that is present in the right? Yes, because its value is 3. Can I go down from here? Yes, I can go because the adjacent value is 3. Similarly, can I traverse this path? Yes, I can because the minimum value for the path is 2. Can I traverse this path? Yes, I can because the minimum value present here is 3, which is greater than 2, which basically satisfies the condition. So similarly, I can travel in this path as well. So basically, what I mean to say is I need to find the maximum value for which I can go from the source to the destination. So for 2, I checked here that yes, I can go. Can I go? So do I want to increase the value from 2 to 3, or do I want to decrease the value from 2 to 1? So obviously, I want my answer to be as big as possible. So what I will do is I will increase the value of 2 to 3 and we'll check whether I can traverse from the source to destination. So let's see. So yes, I can travel from the source to destination if my maximum or the minimum safe value, not maximum, the minimum safe value that can be there in my path is 3. So can I, I can go with the value 3. Now let me increase and check whether I can go with the value 4 or not. So I will try to visit. So I will try to visit from 4. I can go to the adjacent cells which are in the left, which are in the right or in the bottom. So after going to the adjacent cells, the values present there or the Manhattan distances are 3 for both the cells. So I cannot go with the value 4 more than one cell. Hence, 4 is not a feasible answer for me. That is why the maximum value that I can have for this matrix is 3. Similarly, I can traverse from 0 to the maximum value that is present in my Manhattan distance grid, which is 4, and check whether I can go with the value 4, or if I can go with the value 4, if I can go with the value 0. If yes, then I will increase my value to 1 and we'll check. Can I go with the value 1? If yes, then I will increase my value and then check. Can I go with my value 2? If yes, then again increase and check with 3. If yes, then again increase the value and check with 4. This is basically a linear way of checking. But what we can do is we can use binary search here and we can do this process in the order of log n time. For a value of mid, which is found using this binary search, I will be traversing the whole array, or in the worst case, I will be using n square time complexity to check whether I can go from the source to the destination. So let's check the time complexity for a single value of mid. And the mid value can vary from 0 to n. How? Let's say we have a matrix of 3 comma 3 and I have a thief here at 0 comma 3 0 comma 2. So the maximum distance which is present here in the cell is 4, so which is near about 3. So we can say that the mid value can vary from 0 to n, and this will give me a value of log n for the binary search, and for one iteration of binary search I will be checking whether I can go from 0, comma 0 to n minus 1, comma n minus 1 in n square time complexity. Hence, the overall time complexity will become we go of log n multiplied by n square, which will lie within the range as the n value will vary from 1 to 400. So let's go through the code and see how this solution has been implemented. First of all, to traverse in a grid, I have taken a directions vector of pair where all the four directions are mentioned. Basically, I will be summing up these values with my current value and check whether the generated value is lying within the range of 0 to n minus 1. And if yes, then I will be moving forward with the cell if it is ready to visit. So in my main function, what I have done is, first of all, I have used this grid distance function, which gives me the Manhattan distance in a form of grid. How have I calculated the Manhattan distance? In this function get distance, first of all, I've taken a q, and then with by using this q and this vector distance, or here I have taken this. Now I am going through the entire grid and checking whichever value is 1. Now for that, the distance uh, vector will have 0 in it for that position, and I will be pushing the coordinates in the queue. I will be using the queue for a BFS traversal, multi-source BFS traversal, and then I will be populating the whole dis array or dis 2D vector. I'm having this counter, which basically gets incremented every single time when it goes from one cell to another cell. And I'm traversing for all the nodes that are present currently in my queue, popping out one by one, traversing for all the four directions, and checking whether the newly generated coordinates are safe or not to traverse, and checking whether the distance is already int max or not. Basically, I have taken the default value as int max because that is not visited, which it represents. Now, if it is not visited, that means I have to visit it, and I will put the value count in it, and I will push the coordinates in the queue. In this way, I will be generating my Manhattan distance 2D vector, which I'll be returning from line number 74 and using here. Now this distance 2D vector is being used for the binary search. Using this for loop, I am just calculating the low and high of my binary search. Then I am using the binary search while loop here to check whether my particular value that I'm calculating in line number 95, whether this gives me a true value from this check function. If it gives me a true value, then I'm storing the answer in my answer variable, and I'm using this check function. This check function is basically implementing BFS within it, a simple BFS traversal, that whether with the value of mid or the values that are present in my Manhattan grid, that should be greater than equals to mid. And in that way, if I'm able to reach the cell n minus 1 comma n minus 1, then I'm returning a true. Otherwise, at the end of the traversal, I'm returning a false. In this way, I will be able to pass all the test cases, and hence, yeah, the solution is getting accepted. Thank you.